If I gave you the following two fractions, you would probably be able to add them without even batting an eyelid. So say I gave you the fractions 2/3, and I had asked you to add that to the fraction 3/5. You would have told me that you need a common denominator, and in this case that would have been 15. You would have changed your numerators, and so the first fraction's new numerator is 10, the second fraction's numerator is 9, and the answer is going to be 19/15. But what would you have done if I had given you 19/15 and I had said to you, now I want you to tell me what the original two individual smaller fractions were that you added together? We're going to practice this together, and this is called finding partial fractions. So let's take a look at an example. In this example, I have got a numerator 3x plus 5 and quite a complicated looking denominator. And the first thing that I want to do is I want to take this denominator and I want to factorize it. So let's factorize it. This is a nice easy trinomial factorizing, and I'm going to get x plus 1, x plus 2. Now if I want to split this into partial fractions, then I need to split it so that I can have something over each factor in the denominator. In other words, it should be able to look like this. Something over x plus 1 added to something else over x plus 2 should have given me my original statement of 3x plus 5 over the common denominator. In resolving what a and b are, the first thing that I'm going to do is I'm going to find a common denominator now for the left and the right-hand side. Now we know that our LCD would be the most of each type of factor, and I've got two nice bracket factors over there. Getting rid of the denominator here, I'm going to have a times by the new factor in the LCD that it didn't originally have, b times the factor it didn't have in its original denominator, and as the right-hand side had both of those factors, I don't write any down when I'm getting rid of the denominator. Now I'm almost able to compare the left and the right of this equation. If I just distribute the a into its bracket and the b into its bracket, I can nicely see that I've got x terms and a constant term. Now let's take a look at this. Can you see that this number added to that number must give me that answer? And similarly, this number added to that number should have given me 5. So what I'm going to do in my next step is I'm going to take this information and I'm going to separate it out. If a times x plus b times x gives me 3x, it stands to reason that a plus b was equal to 3. And then working with the constants, if 2a plus b is equal to 5, I've now happily reduced both of these statements to two equations, two simple equations with two variables, and I'm now able to find a and b. Get a on its own in equation 1, and that will be equal to 3 minus b. Substitute this expression for a into the other equation, which means that I've got 2, 3 minus b plus b is equal to 5, and solve for b. So I've got 6 minus 2b plus b is equal to 5. If I take my constants to the one side, I'm going to take the 6 across to the side where the 5 is, and so now On the left-hand side, I'm going to have minus b. On the right, I'm going to have 5 minus 6, which is minus 1. So therefore, b is equal to 1. Now I can see that a is going to be 3 minus this value that I've just found for b, and so a is 2. So therefore, if I had partial fractions for my original statement, I could have written these two individual fractions as 2 over x plus 1, then with the b value over x plus 2, which was in fact equal to 3x plus 5 over x plus 1, x plus 2. Now this has been quite a long process, but luckily for us, there is actually a shortcut, and I'm going to show you that now. So with the shortcut, I'm going to start with my original statement on its own. So let's write it down, and as I'm going to show you a shortcut, I'm going to do it in a different color. So I've got 3x plus 5, and then that is over, oh, let's take a blue line. There we go. Going back to blue. X plus 1, x plus 2. To find the partial fractions using this method, it's called the cover-up method. Now what I'm going to do, and I'm going to use this blue box, you could use your finger, is I'm going to cover up one of my denominator factors. The factor that I covered up was the factor x plus 1, so that is when x is equal to minus 1. Now what I'm going to do is everywhere where I see an x, here and here with what has not been covered up, I'm going to substitute in minus 1. Now 3 times minus 1 is minus 3, plus 5 is 2, and minus 1 plus 2 is 1. So it stands to reason that the answer that I get after I've covered up is going to be the number 2, and that number 2 is over the covered up factor. Let's try the other one. This time I'm going to cover up this factor over here, and when I work with this one, then I'm going to get that when x plus 2 is the factor, x would have been minus 2. Now I'm going to substitute minus 2 into the x here and the x here. What I get as my answer, I get minus 6 over, minus 6 plus 5 minus 1 over minus 1, and that answer is 1. So clearly the answer that I've got here is going to be plus 1, but this has got to be over the covered up factor, so that is going to be over x plus 2. Let's look back at what we got before, and you'll see that you got exactly the same partial fractions. But gosh, was that not a lot easier? Just to make sure that my color coding is correct, I'm going to highlight that with yellow too, so you can see where I did my substitutions. So for the cover-up method, I reduce my denominator to linear factors. I cover up a factor. I put that number's solution as a substitution into what has not been covered up, and the answer goes over the covered up factor in each case.